Hello, my dear students. In the last class, we have already discussed about green chemistry. What is the need for green chemistry? What are the goals? And what are the limitations of green chemistry? Today, we will discuss about 12 principles of green chemistry in detail. We know green synthesis is one in which the use and/or generation of hazardous substances as well as production of waste are reduced to an optimum minimum. Adherence to the 12 principles of green chemistry is the essential criterion for designing a green synthesis. The first principle of green chemistry is that waste prevention instead of remediation. A typical chemical process generates products and wastes from raw materials such as substrates, solvents, and reagents. If the efficiency of the process is low or if said reactions occur, the waste generated are generally greater than the desired products obtained, resulting in a loss of valuable substrates and reagents. Waste disposal of polluting and hazardous waste in particular also can be a very costly process. The figure shows a schematic diagram of a chemical process. We know a typical chemical process produces a large amount of waste. So everything possible has to be done for waste prevention rather than seek remediation of the situation after producing waste. One simple example to illustrate the point is with regard to the experiments carried out in schools, college and research laboratories. Most often, these experiments are carried out at a macro scale so that the waste produced are also at a macro level. Green chemistry advocates designing and carrying out experiments at the semi-micro scale or if possible at the micro scale using as small quantities of substrates and reagents as possible. This step produces a massive minimization of waste. For example, inorganic analysis of cations can be performed using spot test using specific reagents rather than carry them out using precipitating reagents which produce bulk quantities of precipitates. The second principle of green chemistry is that atom economy or atom efficiency. Better percentage yield of the desired product in a process is not a criterion for a green synthesis. We know several of the reactions proceed with great efficiency with regard to the percent yield of the desired product. Then how to calculate the percent yield? Percent yield is equal to actual yield divided by theoretical yield into 100%. If 100% or even 85 to 90% yield of the desired product is obtained in reactions, most synthetic chemists are happy. But such a synthesis need not always be a green synthesis because of the byproducts produced which are wasted. For example, consider the Grignard synthesis of 2-butanol from 1 mole of acetaldehyde and 1 mole ethyl magnesium bromide. Even if the theoretically expected 100% yield of 2-butanol is obtained, 1 mole of MgOHBr is produced which is not isolated for any purpose and hence is a waste that is just discarded. So the above synthesis is not a green synthesis. The concept of atom economy, better atom economy is a criterion for green synthesis. The concept of atom economy or atom efficiency developed by B.M. Prost evaluates how much of the reactants of a reaction gets incorporated into the final desired product. It is considered in terms of percent atom economy or percent atom efficiency, which is equal to relative molecular mass of desired products divided by relative molecular mass of all reactants into 100. For example, consider the addition reaction between 1 mole of propane and 1 mole of hydrogen in the presence of nickel catalyst to yield 1 mole of propane. Here, relative molecular mass of propane is 42, relative molecular mass of hydrogen is 2, relative molecular mass of propane is 44. Therefore, percent atom economy is equal to 100%. The above reaction is seen to be 100% atom economical since there are no other byproducts. Like an addition reaction, an organic rearrangement reaction would also be 100% atom economical. However, neither substitution reactions nor elimination reactions would be 100% atom economical because there would be products other than the desired products. The greater the percent atom economy, the lower the amount of waste produced and the greener the synthesis would be. The third principle of green chemistry is that the minimization of the use and production of hazardous and toxic chemicals. That is, use and production of less hazardous and less toxic chemicals. One of the most important purposes of designing a green synthesis is to minimize the use and production of hazardous and toxic chemicals because they cause environmental pollution and are harmful to all sorts of organisms. Now, let us consider one of the commercial methods employed for producing adipic acid. Adipic acid is an important chemical used in the manufacture of a variety of industrial products, including lubricants and plasticizers. Here, the starting material is the benzene, which converted into cyclohexane, then undergo oxidation, and we get cyclohexanone and cyclohexanol, which is then converted into adipic acid. Here, the starting material benzene is carcinogenic and thus highly hazardous. It is produced from a non-renewable source, namely coal. The use of nitric acid as oxidizing agent produces nitrous oxide as a byproduct, which is not only greenhouse gas but also is one of the culprits responsible for the destruction of stratospheric ozone layer. Thus, the process is altogether not environment friendly. Green synthesis of adipic acid starting from glucose has been developed with the use of biocatalyst, namely genetically altered Escherichia coli bacteria and some enzymes in aqueous media. Here, glucose is totally non-hazardous substance. Moreover, the used Escherichia coli bacteria is a harmless strain. Here, D-glucose is converted into 3-dehydroshikimic acid by Escherichia coli bacteria. Then it is converted into protocatechuic acid, which is then converted into catechol by the use of pyrocatechuate decarboxylase enzyme. Then the catechol is converted into cis muconic acid by the use of catechol 1,2 deoxygenase enzyme. Then the cis muconic acid is converted into adipic acid by the use of hydrogen in the presence of platinum. This is the green synthesis of adipic acid. Today we have discussed about three principles of green chemistry: waste prevention instead of remediation, atom economy or atom efficiency, and the minimization of the use and production of hazardous and toxic chemicals, and some examples for that. In the next class, we will discuss about other principles of green chemistry. Thank you.